and if we're successful with this recording, you'll get the recording as well as the notes. So if you find that helpful, you can go back and look at it. So word problems are the things that people really don't like about algebra, right? They seem contrived, like, you see all these little cartoons with jokes, about algebra, go solve your own problems, things like that, or you see, somebody circles the x and says, see, I found x. Nobody really likes this kind of thing where you're asked really kind of dumb questions, things that you would know, like, if I'm 3 times my brother's age in 1960, what was my brother's age in 1952? Those kinds of questions just seem kind of contrived, and they are, admittedly. But what we have here with these word problems is that they do follow at least the form of what you usually will come across. And so the practice here is really being able to take a couple sentences and translate it into some algebra that you can find a solution to. And so that's what we're going to do. The problems are all dumb and they all kind of seem silly, but if you learn this method of doing it, then when you get into a biology class or some other kind of class, then perhaps the kinds of questions that you will get on an ordinary basis would seem a little bit more tractable, a little bit more doable. Okay, so the thing of it is that nobody's ever going to ask you for x or find x or anything like that. And so anytime you're going to apply math in the real world, they're going to be essentially word problems, right? Nobody's going to take an equation out of their pocket and say, solve this. All the years I was an engineering manager, business manager and all that, I've never asked, nor have I been ever asked to find a variable. It's normally what's the sales forecast for next month, or what size of a pipe do we need for this or that, and so you get ordinary language questions, and we're going to focus on giving ordinary language answers to this. So I think I mentioned this on Wednesday. We're going to use 5 steps. Okay, so what you need to do is, the reason why I like this format a lot is because usually what you'll have to do is you'll have to show others how you arrived at your solution. Nobody's going to really ever take your word for anything you come up with, and so you want to be able to whip something out and say, okay, this is how I did it. This is the basis of my my calculation. Now, the other thing that happens is that whatever profession you end up in, you end up working on the same problem over and over. You don't get a whole lot of original stuff. A lot of it is redoing the same problem several times. And so if you have good documentation on how you solve problems, the next time you have to solve the same problem, it's a lot easier, obviously. And so the other thing that happens is you never just sit down and work a problem. Oftentimes there's pieces of information that are missing that you need to find, and so you set the problem aside, you go ask a question, you go do some research, do a measurement or two, things of that sort. So, part of this framework is, to not let you drive ahead of your headlights and really focus on, what you can do and what you can't do. So definitions of variables, defining constants and things like that become pretty important, and we'll be able to discover the timing that we need to do those things. And then the other thing that is really helpful is that oftentimes this is like the first point, but oftentimes you need to present your findings, especially if you end up in a technical field. You're going to come up with presenting your findings to people who don't have a clue on how you arrived at that. And oftentimes just giving an outline of the process that you went through will not only give those people some insight into how you do it, but it will lend to your credibility, that people don't question the fact that, does he really know what he's doing? Well, if you have, a good, work to show for it, then of course that'll be more convincing. Okay, so let's go through a very simple problem here, and I'm going to break this down into 5 steps. All right, so the first step, what you need to do is you need to gather the data and make a model. So you have some sort of statement of the problem, or somebody's orally asked you that, or you find problem 14 in the book or something of that sort. What you want to do is kind of assemble all your data, put together a model, or essentially sketch out your thinking of what this problem entails. Okay, so let's say you bought a sweater. Here's a real simple problem, but we're going to use it with all 5 steps. So you bought a sweater for 56 bucks, and it was on sale for 30% off. What was the original price? Now you can zip right to a little calculation and calculate this really quickly. And so maybe it's contrived in that respect. But I want to take it step by step to show you, how it all fits together. So the first thing in making this model is that we're going to say, okay, let's think about this. We have an original price and we subtract a discount and we get a discounted price. Okay, so notice I put the dollar sign by the discount. We know the discount's in percent, but we don't know it in dollars yet. Okay, so the other part of our model is we say, okay, the discount in dollars is a discount rate times the original price. Now here's a key part of the thinking. When you just go to calculate using 56 and 30, what numbers do? Do you divide that? Do you multiply it? Do you take 1 minus 0.3? All this kind of stuff. If you lay it out here, we're starting to assemble a little bit of an equation that will let us address this problem. So if we combine the two, what we get is we get this original price minus the discounted rate in percent times the original price equals the discounted price. So essentially what I did was I took this first one here, you see, and this was the thing I didn't know. I didn't know the discount in dollars. I knew it in percent, but I knew how to relate my discount to a discount rate, which I have. And of course, I don't know the original price, but at least I know that's going to be in the equation. So I just dropped it in here where I had discount before. And this looks very much like an equation, but it's kind of a map of your problem. Now, in different kinds of problems, like in a geometry problem or something, you might want to draw a sketch or something of that sort, like if you want to find the height of a building based on its shadow or any of those kinds of things that we'll get to. So it may be a word-type model, and the book shows a lot of these, or it may be a diagram with some formulas that let's say the Pythagorean triangle and things of that sort. But this is essentially step one, is gather the data. We know we have a 56 and we have a 30% in there, and here's the relationship that we're going to be working from. Okay, so the next step, and this is the one that I really want to emphasize that you got to do. Okay, if I see variables without definitions, I'm going to circle them in red, and I'm going to say, what's x? Okay, so this is the model carried over from the previous slide. And so you just start making a list. You just read your model from right to left, and you say, okay, the original price. I'm going to say that's P. All right, P is the original price. Put the units, dollars. Now the discount rate, well, I'm not going to define a variable because I know it, right? The discount rate is 30%. Now, anytime we're dealing with percentages in a computation, we're going to deal with the decimal form of it, not the percentage form. So I'm going to write that as 0.3. And then we're going to say, okay, the next box over is the original price. We already have that defined as P. And then we have the discounted price, and we know that you paid $56 for that. Okay, so there it's labeled with dollars again. Now here's the point where you examine this. Is this all going to hold together? Now with dollars, we always deal in dollars, not so much in cents. But if we're dealing with a measurement, like are all our measurements in the same unit? Are we dealing entirely in feet, or dealing with a mix of feet and inches and yards and things of that sort? So we can refine these numbers and do some unit translation if we need to basically make everything work together, and will save us some steps later on in terms of translating units. Okay, so we have our variables. So what we want to do now is we want to write the equation. You see how this kind of falls together now. You have this model, you have all your variables, and so you just go from left to right, and I can write, okay, P minus 0.3P equals 56. Pretty straightforward. So here's your equation. So these are the first three steps, all right? So you start with a problem, now you have an equation to solve, and you have variables in that equation that are defined. So now we're just going to solve the equations. Okay, and then we're also going to check them, all right? So here we're going to just do some basic algebra, and we're going to say, okay, P minus 0.3P is 0.7P equals 56. And then divide 56 by 0.7, and that's going to be the same as 560 divided by 7. which is now 80. Okay, and then I'm going to check it by putting it back in the original equation. All right, that works. 0.3 times 80 is 24, so we get 56. And so now we feel like we're done. Okay, it feels like the equation's solved, we have a value, but now we need to answer the question because that's the point of all this. Now you could run down the hall and whoever asks you this question, you can tell them orally, but for us we want to actually answer the question. And there's a couple of things that we want to make sure that we do. Number one is reread the question. You may be calculating something that's close to but not exactly what you're looking for. For example, if you're trying to find the dimensions of, let's say, a table or something where you have L for the length and W is the width, you reread the question, maybe they're only interested in the width, and you've solved for the length. And so you're making sure that you're going to answer the right question. And then also make sure the units are right. If somebody's going to ask you something that suggests you want a time unit in seconds or in hours, or maybe they want a unit that's on the clock, like 3 o'clock or 3:30. You want to be able to translate that so you're answering the question directly. And so the answer to this was the sweater was originally priced at $80. Okay, so simple problem, admittedly, but with those 5 steps, you're laying it out. You don't ever have to think ahead of what you're doing at present. So you think about, okay, what are the relationships? Make the definitions, formulate those equations, and then you solve the problem. Okay, so some tips. All right. When you're working these, you don't need to label the problems. I mean, you see what you're doing. One naturally blends into the next, and so you don't have to say step 1, step 2, step 3. But keep it in mind, all right, because that's the way I'm going to be grading your papers. And then step 1, of course, doesn't have to be this block diagram with this semi-equation or whatever. It can be a sketch and some general formulas. Like if you have a triangle, you can write, here's the triangle, label B for the base, H for the height, and write your equations, and do all the things that gather your data. And oftentimes a diagram is really the way to crystallize how you're going to solve the problem. So spend as much time as you can on making that diagram complete. Label all the values write all the variables, do all those kinds of things. We're not looking for great artwork here, just basically a nice conceptual formalization of it. And then, we overuse X. I think I mentioned this on Wednesday. Use letters that directly remind you what they're talking about, like L for length, W for width, P for price, T for time, all those kinds of things. And you can use subscripts if you have more than one, like L1, L2, L3 if you like, or start using other letters. And then, so for tests and quizzes, this is always the question, is how am I going to score these? Because, word problems traditionally carry more weight than, a shorter problem. So your score is going to be mostly on the process. How well do you organize your data? How well do you define your variables? How well do you set up equations? And of course, solving the equation, and then answering your question in a plain English sentence. So if you just give me x equals 5, because you can see the answer, like perhaps on this one, if you're good at percentages, you can do this one in your head and you come up with $80. If all you write is $80, you're going to get less than 1/4 of the credit on here. So I really want to encourage you to write out everything in an organized, readable fashion. All right? Like I said, you don't have to label the steps, but it should be pretty evident of what you're doing. You're going, your diagram, your variable definitions, and what I found is that most people have the most difficulty writing the list of variables, carefully defining them. But that's also the most important one, because if you put the correct units, then it makes it much more clear what you're working at. Like you've all seen those problems where you have 5 coins in your pocket. They're quarters, nickels, and dimes, and you want to find out how many of each you have based on the total value, you know, those kinds of problems. So if you say N is nickels, make sure you're knowing your label is clear that that is, N is the number of nickels, as opposed to N is the value of the nickels. And so, you know, asking yourself those kinds of questions will really set up your equations more carefully. So you ultimately could come up with an equation like, if N is the number of nickels, D is the number of dimes, and Q is the number of quarters, you can say something like 0.1 D plus 0.05 N plus 0.25 Q equals the value of all the coins. Okay, so in the definitions, they kind of assemble themselves. Okay, so I have a few problems for us to work. You see, it didn't cut out at all.
Yeah.